Your hands grip the controls of Germany's most feared tank, the Panther. 45 tons of sloped armor and killing power sits beneath you. This is the machine that American tankers dreaded facing across the battlefields of Europe. The tank German propaganda claimed was invincible. You've just captured it intact near the German border, and for the first time, you're about to discover what this beast can really do. The engine roars to life behind you. Smooth, powerful, 690 horsepower of Maybach engineering. You engage the transmission and the Panther lurches forward. This is it. This is what it feels like to command the enemy's finest weapon. The ride is surprisingly smooth. The interleaved road wheels absorb terrain like nothing you've experienced in a Sherman. The optics are crystal clear. The gun, that legendary 7.5cm KUK-42, sits ready to engage targets at ranges your 75mm could never touch. For the first few hours, you understand why German tankers felt superior. This machine feels like a predator. But then, 93 miles into your evaluation, something happens. A grinding sound erupts from the drivetrain. The Panther shudders. You try to keep moving, but the controls lock up. The transmission refuses to engage. Within minutes, this technological marvel transforms into 45 tons of immobile steel. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. What you've just experienced was the Panther's fatal flaw, the same catastrophic failure that crippled hundreds of Panthers across Europe. The same mechanical defect that German engineers knew about but could never fix. The same weakness that turned Germany's supertank into one of World War II's greatest strategic failures. Welcome to the true story of the Panther, where impressive specifications met engineering, reality, and reality won. December 1944. American forces pushed deeper into German territory following the breakout from Normandy. Tank recovery teams and forward units began capturing Panthers with increasing frequency, not knocked out by gunfire, not destroyed by mines, simply abandoned by their crews with engines cold and fuel tanks still containing diesel. Some were found with transmission fluid leaking from the final drive housings. Others sat motionless, their crews having fled when the drivetrain seized during retreat. The U.S. Army Ordnance Department wanted answers. Intelligence reports indicated the Panther outmatched the Sherman in nearly every technical specification: frontal armor, gun penetration, optical equipment, speed on good terrain. American tankers sent desperate messages to Eisenhower complaining about facing technically superior German armor with inadequate equipment. But then recovery teams started bringing intact Panthers to testing facilities, and the real picture emerged. The first comprehensive American evaluation of a captured Panther took place at a forward testing facility near the German border in early 1945. The tank had been captured intact after its crew abandoned it during a retreat. External inspection revealed no battle damage. The armor showed no penetrations. The tracks were intact. The fuel tanks contained diesel. Everything looked operational. American tankers climbed inside to conduct the evaluation. Initial impressions were mixed. The interior was cramped and dark compared to a Sherman. The gunner's position was more confined. The driver's controls felt stiff and unresponsive, but the optical equipment was immediately impressive. The Turmzielfernrohr 9D gun sight provided magnification and clarity superior to American equipment. The binocular rangefinder in the commander's cupola offered excellent visibility. They fired up the Maybach HL 230P30 engine. It started smoothly. 690 horsepower roared through the engine compartment. The sound was different from a Sherman's engine, higher pitched, more aggressive. The Germans had engineered power, that much was undeniable. The testing crew planned a comprehensive evaluation. They would drive the Panther over varied terrain, test the transmission through all 7 forward gears, evaluate the turret traverse system, assess the gun's performance, compare everything to Sherman capabilities. The first few miles went smoothly. The Panther accelerated well on hard surface roads. The suspension provided an excellent ride. The interleaved road wheels, overlapping like scales on a fish, absorbed bumps and irregularities in the terrain better than the Sherman's vertical volute spring suspension. On paper, this was impressive engineering. The steering system, using a dual radius turning mechanism, allowed for gentle turns or sharp pivots, depending on the radius selected. Panther felt fast, not as nimble as a Sherman, but powerful, like controlling a heavyweight boxer instead of a middleweight. The tank's length, 29 feet including the gun, made it feel less maneuverable in tight spaces, but on open ground, it covered distance quickly. German tankers had trained to use this speed for hit-and-run tactics. Engage at long range, fire, then reposition before the enemy could respond effectively. The testers pushed the Panther through various maneuvers: acceleration tests, braking tests, turning radius evaluations, cross-country movement. Everything performed within expected parameters for the first 60 miles. The transmission shifted through its 7 forward gears, though the shifter required significantly more force than a Sherman's near-automatic synchromesh transmission. Each gear change felt like fighting the machine. German tankers must have developed strong arms just operating the controls. Then they tested the turret traverse system. Early RSFD models used a single-speed hydraulic traverse powered by the main engine. Later, RSF-A and G models, like this captured example, featured a dual-speed system with high and low gear ratios. At 2500 RPM in high gear, the turret could complete a full 360-degree rotation in 17 to 18 seconds. This was faster than a Sherman at maximum speed. But there was a catch, a significant one. The traverse speed varied constantly with engine RPM. If the driver throttled back, the turret slowed proportionally. If the engine died during combat, the turret could not traverse at all, except through manual cranking, an agonizingly slow process requiring over 700 turns of the hand crank for a full rotation. The Sherman's electric traverse motor, powered independently from the main engine, rotated the turret in 15 seconds consistently, regardless of engine speed. If the Sherman's engine died, the auxiliary generator kept the turret, traverse motor operational. This difference revealed a fundamental design philosophy gap. German engineers optimized for maximum performance under ideal conditions. American engineers optimized for consistent performance under varied conditions. The Panther's theoretically faster traverse meant nothing when tactical situations required turret movement while the engine idled or during engine restart procedures. The Sherman's slower but constant traverse provided reliability when it mattered most. Mile 70 approached. The testing crew noticed something, a vibration through the hull. Subtle at first, then increasingly pronounced. The driver reported unusual resistance in the controls. The Panther had been operating continuously for several hours. German operational doctrine called for periodic cooling breaks, but the American crew pushed forward to assess sustained operational capability. This was, after all, a combat evaluation. Real battlefield conditions meant sustained operations without convenient rest periods. Mile 80. The vibration worsened. A grinding sound emerged from somewhere in the drivetrain. Not loud, not yet, but distinct. The tank commander ordered a halt. The crew dismounted to inspect the vehicle. They checked the tracks for damage. Nothing. They examined the road wheels, all intact. They looked under the hull for fluid leaks. Nothing obvious. External inspection revealed no apparent problems. They climbed back inside and continued the evaluation. Perhaps it was just a transient condition. Perhaps it would resolve. Mile 85. The grinding intensified. The controls felt increasingly stiff. Something was definitely wrong. Mile 90. The Panther began to shudder during acceleration. The transmission engaged roughly. Gear changes required even more force than before. The entire drivetrain felt like it was binding. Mile 93. The final drive failed catastrophically. The grinding sound erupted into a shriek of metal on metal. The Panther lurched violently. The controls locked completely. The driver tried to keep moving, but nothing responded. The tank rolled to a stop under its own momentum. Attempts to restart forward motion produced only horrific grinding noises from the final drive housings. The evaluation was over. 93 miles. That was all this Panther could manage before complete mechanical failure. The crew dismounted and examined the final drives. These were the units that transferred power from the transmission to the track drive sprockets on each side. The housings were noticeably hot, too hot to touch. When they removed the inspection covers, the damage was immediately apparent. The gears inside had destroyed themselves. Metal fragments littered the bottom of the housing. The gear teeth showed severe wear and stress fractures. The bearings had seized. The entire assembly was a total loss. This wasn't battle damage. This was mechanical failure, pure and simple. The final drives had operated for 93 miles and then disintegrated under normal operational stress. The American testing team documented everything. They photographed the failed components. They measured the wear patterns. They analyzed the metallurgy. They wrote detailed reports. Their conclusion was devastating for German armor superiority claims. The Panther's final drives were fundamentally inadequate for the vehicle's operational weight. The technical cause was clear once they examined the design. MAN, the primary Panther manufacturer, had originally specified epicyclic planetary gearing for the final drives. This gearing type, used successfully in many heavy vehicles, could handle high torque loads with good reliability. But epicyclic gears required specialized cutting machinery that German industry lacked in sufficient quantity during wartime. To accelerate production, MAN changed the design to double-spur gear systems. These could be manufactured on conventional gear cutting, machines widely available in German industry. The change solved a production bottleneck but created a catastrophic reliability problem. Double-spur gears experience higher internal stress and impact loads than planetary gears. They're adequate for lighter vehicles but marginal for heavy tanks. The problem compounded during development. The Panther's design weight began at 30 to 35 tons. This was the weight for which the drivetrain, including the final drives, was originally engineered. But Hitler personally intervened during development, demanding additional armor and a more powerful gun. The production Panther weighed 45 tons, nearly 30% heavier than the drivetrain was designed to handle. The final drive housings flexed under this excessive load. The gears inside bound up, generated extreme friction, overheated, and destroyed themselves. The average lifespan was approximately 150 kilometers, 93 miles. The American testing crew, Panther, was discovered what German field units already knew. The Panther was a mechanical catastrophe waiting to happen. German military documents confirmed this disaster. General Heinz Guderian, Inspector General of Armored Troops, wrote in June 1944 that the lifespan of the Panther's motors, 1,400 to 1,500 kilometers, is significantly higher than the Panther's final drives. A solution to the final drive problem is urgently needed, but no solution ever came. The design flaw was fundamental and unfixable without a complete drivetrain redesign. German industry lacked the time and resources for such a redesign, while the war consumed everything. Eastern Front reports documented the carnage. A March to April 1944 report stated that since the 1st of March, 13 final drives were replaced in 30 Panthers. A January 1945 Panzer Commission report listed 370 defective final drives from Panthers requiring replacement. Analysis of Panthers abandoned in Normandy showed that half of all mechanical failures involved final drive breakdowns as the primary cause. The Panther was eating itself alive. American ordnance teams captured additional Panthers for testing. Each one told the same story. Brief operational periods followed by catastrophic mechanical failure. One Panther, captured near Aachen in October 1944, managed 112 miles before final drive failure. Another, captured during the Battle of the Bulge in December 1944, failed at 87 miles. A third, captured in the Ruhr pocket in April 1945, lasted 121 miles before the transmission ceased. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The pattern was undeniable and consistent. Panthers could not sustain operations. American tankers who had feared these machines realized the truth. The Panther was a strategic liability, masquerading as a tactical asset. Yes, it could kill Shermans at long range. Yes, its armor could deflect 75mm rounds from the front, but none of that mattered if the tank broke down before reaching the battlefield or became immobilized during combat operations. Compare this to Sherman reliability. American testing of Sherman final drives conducted at Aberdeen Proving Ground in Maryland documented operational lifespans exceeding 5,000 kilometers under normal conditions. Soviet tanker Dmitry Loza, hero of the Soviet Union, who commanded American-supplied Shermans on the Eastern Front, stated directly in post-war interviews that the service life of the Sherman track was in excess of 5,000 kilometers. The Sherman's final drives, transmission, and engine were designed for sustained operations and delivered that reliability in combat. The French Army, which operated captured Panthers post-war in the 501st and 503rd Tank Regiments from 1946 to 1950, conducted the most thorough evaluation of the Panther's mechanical reliability. Their 1947 technical report, titled Le Panther, documented every failure and operational problem. The report stated definitively that the truly weak spot of the Panther is its final drive, which is of too weak design and has an average fatigue life of only 150 kilometers. French tankers experienced the same failures American testing crews discovered. Final drives failed repeatedly. Replacement final drives failed just as quickly. The French army had access to captured German spare parts and even employed former German technicians to maintain their Panthers. It made no difference. The design was fundamentally flawed, and no amount of maintenance expertise could overcome that flaw. The British conducted similar evaluations post-war. British forces captured numerous Panthers during the Northwest Europe campaign. After Germany surrendered in May 1945, British authorities commandeered a Panther assembly facility at Hanover and forced the completion of 9 additional Panthers using existing components and German technicians. These British-built Panthers, completed in spring 1946, were subjected to standard British tank acceptance trials. The trials had to be halted, not because testing was complete, but because the Panthers kept breaking down. The last operational Panther damaged its transmission during a hill-climbing test. All other Panthers had already been cannibalized for spare parts or had experienced mechanical failures that rendered them inoperable. The British report, dated February 1948, concluded that very little information of any value was obtained due to the general mechanical unreliability of the Panther. Think about what this means. British engineers and technicians, working with German expertise and captured spare parts in peacetime conditions with no combat damage or fuel shortages, could not keep Panthers operational long enough to complete basic acceptance trials. These were the same trials every British tank had to pass before entering service. Panthers couldn't pass them. The supposed superior German engineering could not deliver basic operational reliability. Soviet forces captured hundreds of Panthers during operations on the Eastern Front. Some Red Army units attempted to use these captured vehicles against German forces. The results were predictable. A February 1945 operation during the Lower Silesian Offensive saw a captured Panther with an experienced crew from 4th Tank Corps, commanded by hero of the Soviet Union Lieutenant Nikolai Ivanovich Dyadenko, used in a reconnaissance mission. At dusk, the Panther passed through forest, attacked from the flank, and destroyed 3 German Panthers in combat. During retreat to Soviet positions, it was hit by German artillery and damaged. After the battle, the tank was written off due to lack of spare parts and mounting maintenance problems. Even when operated by a skilled, decorated Soviet tank ace, the captured Panther proved unsustainable. The Soviets concluded Panthers were not worth maintaining. They had their own 34 and IS-2 tanks which, while less sophisticated in some respects, operated reliably under harsh conditions without constant mechanical failures. Polish resistance fighters captured 2 Panthers during the Warsaw Uprising in August 1944. They used these vehicles to destroy German machine gun nests and even liberated the Gęsiówka concentration camp, freeing 348 prisoners. The captured Panthers performed brilliantly in these initial operations. Then, within days, both Panthers became immobilized due to lack of fuel and battery failures. The Polish fighters had to set them on fire to prevent recapture by German forces. The Panthers' tactical effectiveness lasted mere days before mechanical and logistical problems rendered them useless. The Canadian Army captured an intact Panther in Italy in October 1944. They named it Deserter and used it in multiple assaults before sending it back for detailed study. Canadian reports noted the same problems: excellent combat capability when operational, but constant mechanical failures and maintenance requirements that exceeded available resources. The Panther's sophistication worked against it. Repairs required specialized parts and knowledge that field units did not possess. American armored divisions developed procedures for dealing with captured Panthers. Use them immediately if fuel and ammunition were available. Drive them until they broke down, which usually happened quickly. Abandon them when they failed. Do not attempt sustained operations. Do not rely on them for critical missions. Treat them as expendable assets with brief operational lifespans. This was the reality of the Panther, not the propaganda. The 93-mile failure of that captured Panther, tested by American crews, revealed a truth German tankers lived with daily. Their supposedly superior tank was a maintenance disaster that could not sustain combat operations. Every Panther crew knew the final drives could fail at any moment. They knew the transmission might seize during maneuvers. They knew the engine could break down far from support facilities. They fought with this knowledge, understanding their tank might betray them before the enemy could. German field maintenance units worked desperately to keep Panthers operational. Maintenance reports from Panzer divisions document the scale of the crisis. Panzer Lehr Division, equipped primarily with Panthers, reported in July 1944 that of 82 Panthers on strength, only 47 were operational. The rest awaited parts or repairs. By August 1944, after fighting in Normandy, Panzer Lehr had only 5 operational Panthers remaining from its original complement. The 9th SS Panzer Division Hohenstaufen, which fielded Panthers at Arnhem in September 1944, reported chronic mechanical failures. Combat losses were severe, but mechanical breakdowns exceeded combat losses throughout the campaign. Recovery teams worked around the clock, retrieving broken-down Panthers, repairing them when possible, cannibalizing them for parts when repair was impossible. The logistics of maintaining Panthers consumed resources that could have been used for other purposes. 1st SS Panzer Division, Leibstandarte Adolf Hitler, one of Germany's elite units, received new Panthers in late 1944 to replace losses. Within weeks, nearly half were deadlined for mechanical repairs. Final drive failures topped the list, followed by transmission problems, engine failures, and electrical issues. The division's maintenance officers wrote reports describing the impossible situation. Replacement parts were unavailable. Repair facilities were overwhelmed. Qualified mechanics were scarce. The strategic implications of Panther unreliability cascaded through German military effectiveness. A tank that breaks down is worse than no tank at all. It consumes fuel getting to the breakdown point. It requires recovery assets to retrieve. It ties up maintenance facilities and personnel. It occupies precious transportation capacity moving to and from repair depots. It demoralizes crews who depend on their vehicle. All this for a weapon that often couldn't reach the battlefield or stay operational long enough to matter. American Sherman crews, by contrast, trusted their vehicles. The Sherman had flaws. Its armor was thinner than desired. Its 75mm gun struggled against heavy German armour at range. Early models had dangerous ammunition stowage that caused fires when penetrated, but the Sherman was reliable. It started when you turned the key. It drove where you pointed it. It kept running mile after mile. The maintenance was straightforward. Parts were available. Repairs could be completed in the field with basic tools and reasonable skill. This reliability difference translated into operational availability. American armoured divisions maintained high percentages of operational tanks throughout the European campaign. Even after heavy combat, tank recovery and repair units had Shermans back in action quickly. The logistics system continuously delivered replacement vehicles when tanks were destroyed beyond repair. German Panzer divisions watched their operational strength decline month by month as losses exceeded replacement capacity and existing vehicles broke down faster than they could be repaired. The 93-mile final drive failure wasn't an isolated incident or bad luck. It was the Panther's fundamental nature revealing itself. German engineers had created a tank that looked impressive on paper, that intimidated enemy tankers when it appeared on the battlefield, that could dominate individual engagements when it functioned. But they had failed to create a weapon system that could sustain combat operations under real-world conditions. And in sustained warfare, reliability matters more than specifications. American ordnance officers studying the captured Panther data reached clear conclusions. Technical sophistication means nothing without mechanical reliability. Impressive specifications mean nothing without operational availability. Tactical superiority means nothing without logistical sustainability. The Germans had optimized for the wrong parameters. They built a tank that won engineering contests but lost the war. The lessons transcended tank design. Any weapon system, any tool, any technology must function reliably under actual operating conditions. Must be maintainable with available resources. Must be sustainable through the logistics chain. Must account for human factors in operation and maintenance. Must integrate with doctrine and tactics. Must be producible in adequate quantities. Technical excellence that ignores these factors produces expensive, sophisticated failures. The Panther's development history explains how this disaster occurred. After encountering Soviet 34 tanks during Operation Barbarossa in 1941, particularly at the Battle of Brody-Dubno in June 1941 and later battles, German High Command panicked. The 34's sloped armour, wide tracks, and reliable diesel engine outclassed existing German tanks. A special commission, the Panther Commission, formed in November 1941 to develop a response. Mann's design was selected in May 1942. The first prototype appeared in September 1942. Production began in January 1943. This accelerated timeline, from concept to production in 14 months, left insufficient time for proper testing and development. Engineers identified problems during trials, including the final drive weakness, but pressure to field the tank quickly meant these issues were postponed rather than resolved. The Panther's combat debut at Kursk in July 1943 was catastrophic. Of approximately 200 Panthers committed to Operation Citadel, many broke down before even reaching the battle. Engine fires, transmission failures, and final drive breakdowns plagued the units. By the end of the first day of combat, fewer than half the Panthers remained operational. Many were abandoned when they broke down because recovery assets were overwhelmed. Improvements followed. The OSF-A model addressed some early problems. The OSF-G model, introduced in March 1944, incorporated more refinements, but the fundamental flaws remained unfixed. The final drive problem persisted because fixing it required reducing vehicle weight or completely redesigning the drivetrain. Neither option was feasible during wartime. German engineers made incremental improvements that reduced but never eliminated the chronic failures. Production totaled approximately 6,000 Panthers between January 1943 and March 1945. This was far fewer than planned and far fewer than German forces needed. By comparison, American industry produced 49,324 Shermans from 1942 to 1945. This 8-to-1 production advantage, combined with Sherman reliability versus Panther unreliability, meant American armored forces could sustain operations, while German forces could not. The cost differential compounded Germany's problems. A combat-ready Panther cost approximately 143,912 Reichsmarks, including armament and equipment. A Sherman cost between $44,000 and $64,000, depending on model, roughly equivalent to 60,000 to 90,000 Reichsmarks at wartime exchange rates. Germany paid more than double per tank and got a less reliable product that required more maintenance and consumed more resources to keep operational. German propaganda tried to compensate for these realities by emphasizing the Panther's tactical superiority. Films showed Panthers destroying multiple Shermans. Accounts described German tankers as superior fighters with superior equipment. The propaganda worked on both sides. German soldiers believed their equipment was the world's best. American soldiers worried they were outgunned and outmatched. But propaganda can't fix broken final drives. By late 1944, as American forces pushed into Germany, the myth of German armor superiority collided with the reality of abandoned Panthers littering the roads. American tankers who had feared these machines discovered the truth through direct observation. Panthers broke down constantly. German crews abandoned them when they couldn't be repaired. Captured Panthers failed after brief operations. The supposed supertank was a mechanical disaster. The 93-mile failure of that American-tested Panther symbolized everything wrong with German armor development during World War II. Engineers pursued technical sophistication over practical reliability. Designers prioritized impressive specifications over sustainable operations. Manufacturers pushed vehicles into production before proper development. The result was a tank that looked fearsome, that performed well in individual engagements when it worked, but that could not sustain the continuous operations modern warfare demanded. Wars are not won by impressive specifications. They are won by sustained operations, by logistics that deliver supplies continuously, by maintenance that keeps equipment functional, by production that replaces losses, by training that provides qualified crews, by doctrine that employs weapons effectively, by reliability that crews can trust. The Sherman excelled at all these factors. The Panther failed at most of them. The final drive that failed after 93 miles of American testing represented 45 tons of wasted German industrial capacity. The steel used in that Panther could have produced 2 Stug 3 assault guns, vehicles with far better reliability and operational availability. The manufacturing hours could have produced dozens of Panzerfausts, simple anti-tank weapons that German infantry desperately needed. The resources invested in Panthers generated less combat power than simpler, more reliable alternatives would have delivered. German tank crews deserved better. They were skilled, brave, and determined. They fought against overwhelming odds with equipment that constantly betrayed them. They watched their tanks break down during critical operations. They sat helpless when final drives failed during retreats. They died. When Panthers couldn't escape encirclements because the transmissions seized, they lost battles not because they lacked courage or skill, but because their equipment failed them at crucial moments. American tankers, conversely, could focus on fighting the enemy rather than fighting their equipment. Sherman crews trusted their tanks to start, to run, to keep operating through long campaigns. This trust translated into confidence and effectiveness. When American armor units received movement orders, they moved. When they needed to sustain operations for days, their tanks kept running. When vehicles broke down, repairs happened quickly with available parts and standard tools. This operational reliability was worth more than any amount of additional armor or gun penetration. The story of the captured Panther failing after 93 miles encapsulates World War II's armor warfare in miniature. Technical sophistication confronted practical reliability. Impressive specifications met sustained operations. German engineering encountered American industrial pragmatism. Every time, practical reliability defeated technical sophistication. Every time, sustained operations outlasted impressive specifications. Every time, American industrial pragmatism overcame German engineering elegance. 79 years after that American testing crew watched their captured Panther's final drive destroy itself, the lessons remain clear. Wars are fought by systems, not specifications. Reliability matters more than sophistication. Operational availability beats tactical superiority. Logistical sustainability defeats technical excellence. The side that keeps fighting wins. The side whose equipment keeps working wins. The side that builds systems rather than weapons wins. The Panther failed because Germany treated tanks as engineering showcases rather than weapon systems. The Sherman succeeded because America treated tanks as components in a complete military system. Impressive. Specifications look good in propaganda films and intelligence reports. Reliable equipment wins wars. The Germans never learned this lesson. By the time American tankers discovered the truth about captured Panthers, it was too late for Germany to matter anymore. That final drive, grinding itself to pieces after 93 miles of operation, echoes through military history as a warning. Technical superiority means nothing without reliability. Sophistication means nothing without sustainability. Impressive specifications mean nothing without operational availability. The Panther looked like a supertank. It performed like a maintenance nightmare. American tankers who feared it discovered the truth and stopped fearing. German tankers who trusted it learned the truth and stopped trusting. The verdict of history is clear. The Sherman won, the Panther lost. Not because of specifications, but because of systems. Not because of armor or guns, but because of reliability and logistics. Not because of engineering elegance, but because of practical effectiveness. 93 miles to failure, that was the reality of the Panther. 5,000 kilometers of sustained operations, that was the reality of the Sherman. The difference between those numbers was the difference between losing and winning the war. When the Panther rolled onto the battlefields of Kursk in 1943, it was meant to be Germany's answer to the Soviet T-34, a weapon that would restore the Wehrmacht's dominance on the Eastern Front. On paper, it looked unbeatable. Its 75mm, KK-42 litres, 70 gun could penetrate virtually any Allied tank at long range. Its sloped frontal armour, inspired by the very T-34 it was built to counter, made it nearly invulnerable from the front. It was fast, it was powerful, and it looked terrifying. To Allied intelligence analysts, the Panther appeared to be the pinnacle of armoured warfare. Reports described it as the most formidable tank yet encountered. German propaganda trumpeted it as proof of Aryan engineering genius, a masterpiece of precision, sophistication, and technological mastery. It was the tank equivalent of a Messerschmitt or a V-2 rocket, sleek, intimidating, and symbolically potent. But beneath that aura of perfection lay the seeds of its own destruction. The Panther was over-engineered for a war Germany could no longer afford to fight. It demanded parts, maintenance, and time that Germany no longer possessed. It was a tank designed by engineers, not logisticians, by idealists, not pragmatists. Every design decision that made it lethal also made it fragile. The final drives, the mechanical linkages between engine and tracks were so weak that they often disintegrated under stress. The complex suspension system that gave it smooth movement also made it impossible to repair quickly. The gearbox was prone to failure, the engine overheated, and early models were known to catch fire spontaneously. German tankers joked bitterly that the Panther could destroy itself faster than the enemy could. The joke was uncomfortably close to the truth. In contrast, the M4 Sherman looked almost humble. Its 75mm gun was adequate but unremarkable. Its armour could be penetrated by virtually any German anti-tank weapon. Its high silhouette made it an easy target. German crews mocked it as a Ronson after the lighter that lights every time. And yet, it was the Sherman, not the Panther, that conquered Europe. The difference lay in philosophy. The American military-industrial complex did not design the Sherman to be the best tank in a duel. It designed it to be the best tank in a system of war. A tank that could be built in the tens of thousands, shipped across oceans, repaired in muddy fields, and kept running for months with minimal maintenance. It was a machine designed for the world's first truly industrial war, not for an engineer's dream. The Sherman's parts were standardized. A mechanic in Normandy could repair a tank using components made in Detroit or Chicago, and they would fit perfectly. Its radial engine was reliable and easy to maintain. Its tracks could be replaced in hours, not days. Its simple design meant that an average crew could be trained quickly and effectively. American doctrine treated tanks not as individual dueling champions, but as cooperative instruments in a combined arms orchestra supported by infantry, artillery, engineers, and air power. The result was a tank that worked. It started in the morning. It ran all day. It didn't need to be nursed, coddled, or prayed over. And that, far more than armor thickness or muzzle velocity, was what won the war. The statistic that defines the Panther's failure is as brutal as it is simple: 93 miles. That was the average operational life of its final drives before catastrophic failure. Imagine an army forced to abandon or repair its most advanced weapon every 100 miles of movement. Imagine the logistical nightmare of keeping spare parts flowing to the front while Allied bombers shredded Germany's transport network. Imagine trying to fight a mobile war under those conditions. The German army did not need better tanks, it needed working tanks. By late 1944, entire battalions of Panthers were immobilized not by enemy fire, but by their own unreliability. German mechanics worked miracles just to keep a handful running. Crews often had to strip parts from disabled Panthers to keep others operational. It was an act of cannibalistic desperation, not military efficiency. The Wehrmacht's logistical system, already collapsing under Allied bombing and fuel shortages, simply could not sustain such a demanding machine. Every Panther on the front line represented a logistical tail that Germany could not afford. Every mile it moved consumed resources the Reich no longer possessed. And so the Panther became what the Germans themselves called a Wunderwaffe, a miracle weapon, precisely because it existed more in theory than in practice. The Sherman, by contrast, was part of a system that worked. It was not the most glamorous weapon, but it was the most available. The US Army understood that a tank that breaks down in combat is worse than no tank at all. A functioning, reliable, average tank is infinitely more valuable than a superior one sitting immobilized behind the lines. Sherman production lines were models of efficiency. More than 49,000 units were built during the war, and they rolled off assembly lines at a rate Germany could scarcely comprehend. Spare parts followed the tanks wherever they went, packed in standardized crates that could be opened and used by any maintenance crew in the world. American supply depots overflowed with fuel, tools, and replacement engines. If a Sherman broke down, it could be repaired in the field. If it was destroyed, another could replace it within days. This system extended beyond the tanks themselves. American logistical doctrine ensured constant availability of fuel, food, ammunition, and manpower. Maintenance units were embedded within combat divisions. Engineers built roads and bridges to keep armored columns moving. Communication lines linked tank units with artillery and air support, allowing for rapid coordination. The Sherman was just one cog in a vast, synchronized machine of war, and that machine never stopped moving. When German units retreated, they left Panthers behind. When American units advanced, they brought their Shermans with them. The result was inevitable. Early in the war, American tank crews feared the Panther. Intelligence reports painted it as indestructible, and first encounters were often disastrous. A Sherman's 75mm gun could rarely penetrate the Panther's frontal armor, while the Panther's gun could slice through the Sherman from over a mile away. Many tank battles in Normandy were bloody, one-sided affairs, at least at first. But as the campaign wore on, the psychological tide shifted. American crews began to notice that many Panthers never reached the battlefield at all. They broke down en route, bogged in mud, or were abandoned for lack of fuel. Those that did fight often had mechanical issues. Crews reported Panthers' thrown tracks, failed transmissions, or overheated engines. A tank that cannot move or traverse is a dead tank, no matter how powerful its gun. Moreover, Allied tactics adapted. Rather than dueling head-on, Shermans used maneuver, numbers, and coordination. Airstrikes, artillery, and infantry anti-tank weapons worked together to neutralize German armor. The introduction of the Sherman Firefly, armed with the British 17-pounder gun, restored balance. Suddenly, the vaunted Panther was no longer an unbeatable monster. It was just another target. German crews, on the other hand, lost faith. They saw their new wonder weapon break down again and again. They fought with dwindling fuel, no replacements, and collapsing morale. The Panther had promised victory and delivered frustration. It was a symbol not of power, but of overreach. At the heart of this contrast lies a philosophical divide between German and American engineering cultures. The Germans prized perfection. Each tank was hand-built, finely tuned, and meticulously assembled. It was a masterpiece of craftsmanship, but it was also expensive, complex, and slow to produce. A Panther required 10 times more labor hours than a Sherman. In an industrial war, that ratio was fatal. The Americans prized sufficiency. Their goal was not to produce the best tank, but to produce enough of a good tank and to ensure that every single one of them worked. They valued ease of manufacture, simplicity of repair, and uniformity of parts. A Sherman was not an engineering marvel. It was an engineering compromise, and that was precisely why it succeeded. Germany's obsession with perfection crippled its war effort. The same mentality produced the overcomplicated Tiger, the temperamental jet fighter, Me-262, and the unreliable V-2 rocket. Each was a triumph of design and a disaster of production. Each drained resources that could have been spent on simpler, more practical weapons. Each reflected a nation still trapped in the illusion that brilliance could substitute for logistics. The United States understood that wars are won not by perfect machines, but by systems that can be built, maintained, and sustained. By 1945, Germany had produced around 6,000 Panthers. The US built nearly 50,000 Shermans. Many Panthers never reached combat mechanical failures, and shortages kept readiness below 40%, while American divisions maintained 80–90%. The U.S. could field 8 working Shermans for every 2 Panthers. With air superiority, steady logistics, and vast manpower, the outcome was inevitable. The Panther was a tactical marvel trapped in a losing strategy. After the war, the Panther's legend grew, but professional soldiers drew a harsher lesson. Post-war, American and NATO designs focused on reliability, maintainability, and logistics principles the Sherman had proven vital. Even the Soviets favored their rugged T-34 over over-engineered rivals. The Panther remains a warning. Technological brilliance cannot compensate for unsustainable systems. Every generation risks forgetting that reliability and scale win wars, not perfection. The Panther embodied the arrogance of a nation chasing ideal machines. The Sherman embodied the efficiency of one that mastered industrial warfare. The Panther looked invincible, but wasn't. The Sherman looked ordinary, but won. One failed after 93 miles. The other rolled 5,000 kilometers to victory. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.